Welcome everybody to the June meeting of the Science and Engineering Council, still online with our monthly Zoom meetings until we're able to resume in person. And speaking of that, we wanted to take some time here at the beginning of this meeting to take a poll while we're doing the introductions about our future meeting formats going forward as in-person events are starting to open up. Cheryl, I think we're ready to put up maybe a couple of Zoom poll questions, and we'll have those up for a little while, and then people can respond. And these questions are pretty straightforward about what your preferences are going forward. So the first question is up. And the first question is, would you be likely to attend SEC lunch meetings if they were held in person starting in August or September? And what would your preference be for attending those meetings, either going back to in-person this fall or in-person lectures that are not luncheons? So lunch or not lunch? Okay. I'll give that a minute. So while you're answering that, I'll introduce board members. Here on this call, I see we've got Cheryl Ebner, Yvonne DeGraw, Bob Lilly, Mary Howe Grant, Steve Skopatz, Bill Ther.
Uh-oh, I lost him.
Theringer, John Fishbar, and my. Sorry,
Okay.
Did I miss somebody?
Back.
Oh, did I go out there for a minute?
Yeah,
Sorry about that.
You glitched out.
Sorry. Okay. Welcoming our new premier sponsor, Minot Enterprises, which joins our existing sponsors, Community West Bank, Bengal Engineering, and Toyon Research Corporation. So welcome to Minot, and thanks again to all of our sponsors. Okay, another poll question. Are we ready for the second one?
Yep.
Okay, the second one is, where are we here? Do we have the second one up?
Well, both of them are on the poll right now.
Oh, that's the second one. It's already up. Sorry.
Yeah.
So this is the preference.
Yeah.
For lunch or no lunch. Okay, so that looks like we've already got the responses there.
Yeah, so we're collecting the responses.
Okay. So if more people chime in, they'll see this. If folks, as they log on, they'll see this, right?
Yeah.
Right. Okay. So we can leave that up for a while. And then we also, before we kick off today, we'll want to recognize some new and recently renewed members, including Richard Church, DC McGuire, John Swift, and Doug Troxel. If anybody there is on this call, welcome. You can raise your hand and say hello. And thank you also to everybody who's donated to the SEC when registering for the event. These donations really help with our administrative expenses and support our science fair awards. Okay, I think with that, Yvonne, I think I can turn it over to you, and we can discuss upcoming programs and introduce today's speaker.
Great, thank you, Tim. Let's see. Our next meeting, just so people can put this on their calendar, will be July 14th, again on Zoom. Our speaker will be Lori Guthrie, who's the VP of Business Development at Carbon Engineering Limited, a provider of direct air capture technology to capture carbon dioxide directly from the atmosphere. They are based in Vancouver, British Columbia, and are focused on the deployment of megaton scale direct air capture technology. So that should be an interesting talk. And we're taking advantage of Zoom by having somebody speak to us from Vancouver, who we didn't really find anybody in town on that subject. Today, we're happy to present this talk by Dr. Christopher Bates, who's an assistant professor at the Materials Department at UCSB. He also serves as the Associate Director of the Materials Research Laboratory, the MRL, at UCSB. Dr. Bates earned a bachelor's degree in chemistry at the University of Wisconsin-Madison and a Ph.D. from the University of Texas at Austin in 2013 under the guidance of C. Grant Wilson. After a postdoc with Nobel Prize winner Robert Grubbs at Caltech, Christopher moved to UCSB in 2016. Professor Bates's research sits at the intersection of chemistry and material science, leveraging synthetic and physical experimental techniques to design, create, and probe the properties of soft matter. His current research includes block polymer self-assembly, thermoplastic and supersoft elastomers, thin film patterning, and dynamic polymer networks. He's here today to speak to us about new elastomers recently developed at UCSB. If you have questions during today's talk, you can type them into Zoom's chat area during the talk or ask them after the talk. So thank you very much. And I'm going to stop my share and let Dr. Bates share his.
Great. Thanks for that introduction, Yvonne. Can you hear me okay?
Yep.
Terrific. So while we're getting the screen sharing up, hopefully everybody gathered from that introduction that the talk will have a little bit for everybody. I know this is quite a diverse group, and so people like Mary may resonate more with the chemistry. Some of you others may resonate more with the engineering, and hopefully everybody takes something away. We're really flexible in terms of questions. If you have them during the talk, please feel free to interrupt, or you can save them until the end, and happy to address them at that point. Can you see the presentation in screen sharing mode?
We see a desktop with, oh, now we do, yes.
Great, great. So the topic today is on elastomers, but before we place these new materials in that context, to step back with an even bigger picture, most plastics and other types of rubbers are predominantly created from linear polymers, which are really long molecules. And we may characterize those, for example, by a degree of polymerization, which is how many repeat units of a monomer there are. How long is the molecule? And the talk today has to do with a different type of polymer architecture, what's called a Bottlebrush polymer. It still has a long polymeric backbone, which is depicted in gray, that has some length or degree of polymerization we're going to call NBB for backbone. But now off of every repeat unit hangs another polymer that we call side chains. And these have a different length called NSC. And using chemistry and synthesis, we can actually control both NBB and NSC separately. As chemists, we have remarkably good control over creating this type of architecture, which has emerged in the last 10 or 15 years. When you make polymers that are these bottle brush architecture in comparison to linear materials, there's very different properties that arise. Well, for example, if you take linear polymer chains and you connect them together in a process called crosslinking, this is like what Goodyear discovered in order to make tires, where the crosslinking reagent was sulfur. There are many other choices for the blue chemistry and for different types of cross-linking reagents. One we'll keep coming back to in this talk is related to a commercial material known as Silgard 184. You buy this as a kit, it's available on Amazon. One of the bottles is a viscous liquid. The other one is a liquid with a little bit of catalyst in it. You mix them together, you pour the material into the shape of a mold or whatever form you want to make your material out of, and then you heat it up in an oven to cross-link it. And because Silgard 184 is made out of polydimethyl siloxane, it has a low glass transition temperature, which means it is rubbery at room temperature, like a tire or like a rubber band. When we start instead with bottle brushes, this unusual branched architecture as the building block, when you cross-link it, you can make a material that's similar in spirit. It's still a rubber or an elastomer at room temperature, but because of the architecture, it's orders of magnitude softer than your typical tire or your typical rubber band. And the way to think about this is with an everyday kind of experience like string versus rope. The lower limit on softness, or how stiff your rubber ends up being, is related to the chains entangling with each other, like you can see string in the lower left. If you fatten up the molecules, you make them have a larger diameter here because of the architecture we encode with chemistry, it's more like a thick piece of rope. And you probably know intuitively from experience, it's a lot easier to tangle up some thin string than some thick rope. And the consequence is a thin string, or your normal linear polymer, will be stiffer than your Bottlebrush polymer, your thick piece of rope, which will end up making an elastomer that's much softer. So that's the topic of today's talk. How do we make these super soft elastomers, and how do we use them in various applications? Now, the motivation is really advanced technology, and these include things like sensors and actuators. If you think about robots, your mental picture of a typical robot is probably some clunky metallic object that can move, that can try to interact with its surroundings, but it's not nearly as adept at doing so as we are. For example, our hands. Our hands are much softer, they're more tactile, they can interact with their surroundings much better. How do you make materials that bridge this gap between today's robots and robots of the future? Or sensors today and sensors of the future? You can see a variety of different sensors pictured on the slides that interact with humans in, say, medical applications, in advanced thermostats in your home, even ones that interact and sense the hydration of plants. And believe it or not, this ubiquitous need for actuation and seemingly distinct devices, sensors, actually can use a common material platform. And that's what we'll discuss today. First, in the context of sensors, this is where we started, but you'll see how it extends to actuators momentarily. And for our purposes, we're interested in a fairly low pressure sensing regime. You can imagine it's harder to sense pressure the lower the pressure it is. You just have less signal available. And here we'll describe this regime qualitatively. We'll define it as about 1 kilopascal of pressure up to about 100 kilopascals of pressure, which is the atmospheric pressure at sea level. And there are a whole bunch of different potential applications in this range. The pressure in your brain is on the lower end, around 1 kilopascal. So is the pressure in your eye. When you interact with your phone, touch sensing can fall within this range, as well as object handling and other things like pulse monitoring. Now, the common material platform we alluded to a minute ago is related to the simplest type of device we probably learned about in introductory physics all that time ago. If you take 2 electrodes and in between you put some material, which is a dielectric, you can control the capacitance of this device through the thickness of the elastomer in between, or the dielectric in between. And if you make the dielectric an elastomer, meaning it's deformable like a rubber band, you can apply pressure to the electrodes. You can physically deform the device and make the electrodes squish closer together, as depicted on the right. And you can measure that change in capacitance because the thickness of that dielectric layer changes. Or you could operate this device in reverse, and you could apply a voltage across the electrodes, and that polarizes the layer in blue, the dielectric. And if it's a polymer, you'll create plus and minus induced charge, and those will attract each other and cause the device to physically deform because you're squishing that elastomer layer using a voltage. And that's a type of actuator. So you can turn pressure into an electrical signal, which is a pressure sensor, or you can turn an electrical signal or voltage into movement, which is an actuator, with the same kind of device. Now, the requirements for that blue elastomer layer in between are contrary to each other. You can optimize one at the expense of the other. You'd like it to be really soft because both of these modes, either the pressure sensor or the actuator, rely on deforming that middle layer. But you also want it to be polarizable. When you apply voltage, you want to create an induced charge, or when you apply pressure, you want the material to polarize, which creates a signal that you can measure. And unfortunately, you can't really do both of these well. If you make something really soft, it tends to be non-polarizable with traditional materials. And if you make something polarizable, like for example, nylon is pretty polar, it tends not to be super soft. So these requirements are in opposition. Now, if you look at this device in cross section, this is just picturing it differently with a focus on the dielectric elastomer layer. And as you probably gathered, we're going to try to use our new Supersoft materials that rely on polymer architecture to control the stiffness. And if you were to do this with a linear network, you apply some force, you squeeze that material down, well, it won't be that soft. It might deform a little bit, but not a ton. Relatively low sensitivity for a pressure sensor. If you put a special super soft elastomer in the middle, made up of these Bottlebrush polymers, you'll be able to deform it more. It'll have a lower modulus or a lower stiffness. The thickness will change more, and you'll have a much higher sensitivity. So that's the idea. Now, for those of you like Mary that enjoy chemistry, you may like this slide. If you don't like chemistry, you can zone out for 30 seconds, but it's kind of neat the way that we make these materials. And it may look complicated, but it's incredibly simple. The simplicity is related to this catalyst we use called the Grubbs catalyst. The way to think about it is this ruthenium center, that's the active catalyst, it's reactive, and it's got all these ligands around it that just tune the reactivity. We're not going to worry about those ligands at all anymore. They're there from years of research that have really optimized the activity of this family of catalysts. And we use a monomer called norbornene. These are two depictions of the same norbornene monomer. It's a bicyclic ring system, which means there's two rings that are fused together. And importantly, it has this double bond in it. So you can see this is more of a three-dimensional picture on the left. This is more of a top-down projection on the right. Importantly, norbornene, because of that double bond being constrained in the ring, it has a lot of ring strain. And so when it's exposed to this catalyst, the catalyst can really quickly react with it. And it can polymerize it to build up a polymer, where our monomer or our building block is norbornene. And the mechanism is as follows. If you're interested, the ruthenium with that double bond to one of the ligands can do a 2+2 cycloaddition and then revert in the opposite way. And if we redraw this, you can see it split open one of the rings. And it's got an active ruthenium center on one side. This thing can then react in the same way with another monomer, where now you've got two repeats with an active ruthenium center on the end. And this process can repeat over and over and over again to build up a polymer with many repeat units. And then when you expose this after the reaction to something like ethyl vinyl ether, which is a liquid, you just squirt it into the reaction, you cleave off this active ruthenium center, you cap it with a carbon, and the polymer chain is done growing. But what we've depicted is growing a linear polymer chain when we start with norbornene. So how do we grow a Bottlebrush polymer, which will make super soft elastomers? We simply start with what's called a macromonomer instead of a monomer. So we take a polymer chain, which is going to become the side chains of our molecule, and we install a norbornene on exactly one of the chain ends. And then we take these macromonomers and we expose it to the ruthenium catalyst. And now every repeat unit has this starting polymer chain, and the ruthenium builds up the backbone by polymerizing these side chains together over and over and over again to some degree of polymerization or length that we call NBB for the backbone. Now, it may sound complicated, but I promise you it's not. Undergraduates in the lab do this on a regular basis. The reactions are very fast. They take of order 1 hour from start to finish. Then you can isolate the polymer. The polymers we'll start with today, again, are like that commercially available product Silgard 184. They're made of polydimethylsiloxane, which has a repeat unit of Si and O, and the silicon has 2 carbons on it. And this is the polymer we'll build up as the side chains, where again, this gray backbone constitutes our polynorbornene that's created from the Grubbs catalyst. Now, polydimethylsiloxane is a really interesting material. It has a low glass transition temperature, one of the lowest, so it's a liquid at room temperature. It's cheap, it's commercially available. It's used in many applications, including biomedical implants, because it's biocompatible. And to get a flavor of how we do this from a synthetic perspective, we will buy a polydimethylsiloxane with a single reactive chain end, in this case an OH, and we'll couple that with a fairly complicated looking molecule, which is actually really easy to make, and it has a norbornene on one end. All of this other stuff is just a linker that allows us to couple it to that reactive hydroxyl group. So the important feature of this molecule is it has a norbornene connected to a polydimethylsiloxane. And then we dump in a little bit of the Grubbs catalyst and we polymerize that norbornene to build up a backbone. And you can follow this reaction by gel permeation chromatography. And to give you an idea of what this data looks like, you inject the polymer that you synthesized into a column that separates it essentially by molecular weight. It really is related to size in solution. So you're monitoring the eluent as it comes out of the column, that's the x-axis, as a function of time. And your detector, in this case a light scattering detector, gives you signal when it starts seeing high molecular weight polymers come out. And so you can see that the signal depends on how long you wait in the experiment, and it also depends on how long a backbone we synthesize, where longer backbones come out first in this characterization method. And you can see here we can systematically control the backbone length. It turns out by the ratio of the macromonomer, so the PDMS with the norbornene, relative to the catalyst, because this is what's called a controlled polymerization. So the details of that aren't so important, other than to appreciate the size of these molecules. If you look at the picture in the upper left, we start with PDMS chains that are of order 5,000 or 10,000 grams per mole, and they have that reactive norbornene on the end. And you link together it can be hundreds of these things, say 200 plus side chains that are each 10,000 grams per mole. So you can appreciate, while these numbers may not seem astronomical compared to other linear polymers, the molecular weights can easily reach into the millions of grams per mole. This is very efficient chemistry. What we've just described is the synthesis of fairly well-defined Bottlebrush molecules. They have PDMS side chains, which is a liquid at room temperature. These molecules are also viscous liquids at room temperature. They're viscous because they're very high molecular weight, but nevertheless, they still are liquids. And what we're really interested in, as mentioned on the second slide, is linking these things together and actually making elastomers, because then you would have a super soft elastomer. So what we're looking for is chemistry that allows us to do this in a simple way, in a tunable way, and in a way that we can start creating devices like the pressure sensors we introduced a few slides ago. To do that, we've turned to some chemistry involving benzophenone. Benzophenone is the molecule depicted here on the upper left. It's actually in sunscreen, which tells you that benzophenone is photoreactive. And when you shine UV light on it, which is what damages you when you're sitting out on the beach, damages your skin, it excites the carbonyl group, so it splits one of the bonds and makes a bis radical species. And this bis radical is kind of neat because it can pull off a hydrogen atom, meaning hydrogen radical, off of pretty much anything, especially alkyl groups and types of functionality that are on the polymers we're making. So when it does that, the hydrogen atom will preferentially bond to the oxygen-centered radical, and it'll leave this carbon-centered radical and a radical where you pulled off the hydrogen atom. And these two radicals can recombine and make a new covalent bond. So we thought this would be a great mechanism to link together Bottlebrush molecules if we designed so-called crosslinkers with the following features. First, you want to have 2 reactive benzophenone groups per crosslinker so that one can link to a Bottlebrush molecule, say on the left, and the other can link to a different Bottlebrush molecule on the right. This is linking them together and creating a cross-linked material. Second, we thought it would be important to bridge these reactive benzophenone groups with something that will allow the crosslinker to mix well with the viscous liquid that's the Bottlebrush polymer. So you can imagine if the Bottlebrush polymer is mostly polydimethyl siloxane, why don't you make that linker in the crosslinker also polydimethyl siloxane? Those two things should dissolve in each other. And indeed they do. So we purchased polydimethyl siloxane, this time with 2 reactive chain ends. There's a hydroxyl group on the left and on the right. And we can do the same kind of linking chemistry with a functionalized benzophenone to simply install it on both sides of the PDMS chain. The processing, once you've got the Bottlebrush, and once you've got this photo crosslinker, is really easy. You just mix them together at room temperature. They're miscible. You shine a little bit of light to activate the benzophenone, links all the chains together, and it's no longer a viscous liquid. And you can see that in this picture where Veronica has stood the sample that's been cross-linked up on its side to show you it's not flowing. We characterize these materials in a variety of ways. One of the really neat ways we do it is with a technique called rheology. We have a rheometer in the materials research laboratory, which is one of the buildings and departments on campus. And the rheometer has a UV light built into it. So rheology in this context, you take 2 parallel plates and you put your material in between them and you rotate one of the plates to deform or apply a strain, kind of rotational strain on the material. And you actually don't go just one direction, you go back and forth with some controlled frequency. And you can learn about how solid is your material, how liquid is your material, or stated in another way, how viscoelastic your material is. And then understand some of its properties, like its stiffness, because if it's stiffer, it's harder to deform the material by rotating. So this experiment is pretty rich in information, particularly when we can shine the UV light on the sample and monitor what happens as it's reacting to undergo this cross-linking. So there's 2 data sets here that both come from the same experiment. There's something called the storage modulus, which is the elastic contribution to the stiffness. And there's something called the loss modulus, which is the viscous contribution. So you can think about this as being in between a liquid and a solid. If it were purely solid, it would just be viscous, elastic. If it were purely liquid, it would just be viscous. Polymers tend to be somewhere in between. And the key point is that at time equals 0 here, you have G double prime, that viscous contribution is much larger than G prime, that elastic contribution. This is a hallmark of a liquid. And that's what we just argued you have. until you shine light on the material. So you start shining light on the material, and you can see that you pretty quickly have that G prime, the elastic contribution, jump up, and it becomes larger than G double prime, which is a characteristic of solidification. So after a couple minutes, 2 or 3, the sample transforms from a viscous liquid into a solid, and then you can see eventually these parameters stop changing. And that tells us that the reaction is complete. And we've got a nice elastomer out here. Now, to put this into context relative to your standard materials like Silgard 184 or rubber in your tire, what we're going to do is just plot that storage modulus, or the elastic contribution, versus the frequency. Remember, we said that we rotate the top plate back and forth, and so we're changing, or we can change the frequency of that rotation. When you plot it like this, if you've got a nice solid, you pretty much should see a horizontal flat line. And the value of G prime at that horizontal flat line is the stiffness in a rotational kind of deformation. And you can see up here for Silgard 184, remember, this is your linear polymer elastomer. The stiffness is up around 10 to the 6th pascals. It's up around 1 megapascal. And I want you to remember that number, because that's a pretty good approximation for as low as you can go with a traditional material. The stiffness, it's gonna plateau and flatten out about 10 to the 6 pascals, or a megapascal. And you can see now, we've made some Bottlebrush polymers. The blue chemistry for the side chains is identical to the blue chemistry of Silgard 184. All we've done is changed how they're linked up together. We've gone to this more complex branched architecture. You can see when you do that, you drop the stiffness down, well, to 10 to the 5 or even 10 to the 4. These are 4 different formulations that we've synthesized. They have different lengths of the backbone. They have different lengths of the side chain. The details aren't so important, other than to appreciate that the Bottlebrush architecture has dropped the stiffness by 10 to 100 times, depending on the exact design that we use. You do this, though, without changing the polarizability. Remember, we said in devices, you want the material to be deformable, super soft, and polarizable. What you're looking at here is the dielectric constant, which is basically the polarizability at different frequencies. And you can see that your standard linear material and your Bottlebrush material basically have indistinguishable polarizabilities. It's all just PDMS. So we're decoupling the polarizability from the mechanical properties using architecture. Now, making these devices, again, is really simple, very straightforward. Parallel electrodes. In this case, we're using indium tin oxide coated polyethylene terephthalate. So they're a little bit flexible because it's a conductor on a polymer. And it's transparent because indium tin oxide is transparent, and so is polyethylene terephthalate. We wire it up to an LCR meter. Here's a picture of the device with those connectors on the right and on the left. If you don't have those connectors, here's an example of the device. You can probably barely even see it, but it's being held by these tweezers in front of the California poppy, which is our state flower, and it's transparent. And you can quantify that using transmittance or using haze. These are measures of the scattering of light or the transmittance of light. Basically, the sensor stack, so all of this stuff combined, has a transmittance, has a transparency, if you want to think about it like that, that's very, very similar to the electrodes we've selected. The electrodes are the ITO-coated PET in green. It's really close across the visible to the sensor stack itself. So our material, that blue stuff, the dielectric elastomer, is pretty transparent. Now, when you push on this device, you measure the change in capacitance, and the y-axis here is that change in capacitance normalized by the original capacitance, which we call C0. Just think about the y-axis as the signal you get out when you push on the device and you deform that soft elastomer in between the electrodes as a function, the x-axis, of applied pressure. And this is that low pressure regime we introduced early in the talk. This curve, which is really like the baseline in the plot, is your standard linear material. If you put Silgard 184 in between the electrodes, you can apply pressure in this range and you really don't get a lot of signal out. But when you go to the Bottlebrush elastomers, and again, these are 4 different samples that have different lengths of the backbone, different lengths of the side chain, you can see a much bigger increase in the signal when you apply the pressure. And depending on where you calculate it, it can be up to roughly 50 times increase in sensitivity, simply by controlling the polymer architecture. You can monitor this in a different characterization tool we have in the materials research lab called a dynamic mechanical analyzer. It's basically a probe, and you can program it to jam into your sample at an applied frequency with a given amount of force over and over and over again. So you can see we're monitoring this signal, or the relative change in capacitance, over and over and over as a function of time when we oscillate with a pressure of 21 kilopascals, up and down, up and down. And these are 2 different materials that we've made, 2 different Bottlebrush elastomers. One of them's kind of medium soft, and one of them's even softer than that. And you can see you get a bigger signal out the softer the material is. The amplitude of the oscillation is much larger. You get a little bit of baseline drift, but even when you do, you have a stable amplitude, up and down, up and down. You can actually go to even lower pressures than that 1 kilopascal we said was very low. So here's 1 kilopascal with those 2 different samples, the kind of medium soft and softest. And you can go down to even lower, lower, and lower pressures. And to orient you with what this magnitude is, 250 pascals of pressure is pretty close to if you've got your device sitting on the table and a fly comes over and lands on it. Now, that's not a lot of pressure, but we can pick that up using this device. Because it's with flexible electrodes, you can physically bend the sensor. You can see here the sensor's been bent. It's taped onto the table. We use this probe that's a hook for no reason other than that's what was available on the tensile tester at the time. So don't worry that it's a hook. We just smash that hook into the sample. And again, when it's bent, you still see a signal or a change in capacitance as a function of pretty low applied pressures. So these are actually nice pressure sensors. This is a photo process. So changing gears a little bit, you can use this to process these types of materials in other ways as well. And just to give you a sense of how, if anybody's familiar with lithography, it's the technique used to create computer chips and disk drives. It's a way of patterning really, really tiny features or lines of metal interspersed with dielectric materials that build up transistors in your computer chip or build up bits on a hard disk drive to store information. And it's all done in thin films on silicon surfaces. So there's these nice big silicon wafers that are 8 or 12 inches in diameter that this is done on. And if anybody has read the news recently, Joe Biden is, in Congress is actually collectively are pushing to put a big investment into the semiconductor industry to maintain national competitiveness. It's this type of process. They use lithography in that industry in clean rooms in order to create advanced technology. We can use these materials in a thin film format in analogous ways because they're light responsive, which is the stimulus used in this type of processing. What you do is take your substrate, like a silicon wafer. You can coat a thin layer of the Bottlebrush polymer on top. This is the uncross-linked material, just the as synthesized viscous liquid. And you take a mask, which is dark in some regions and transparent in other regions, and you shine light through that mask. You can make the mask have a pattern, meaning the transparent regions have different shapes that you can control. Where the light hits the Bottlebrush thin film, it cross-links like we've seen before, because there's a little bit of benzophenone in there. Where it doesn't hit the film, no reaction. You can take this material that's had light shined on it, and you can dissolve away the uncross-linked material in water. Anywhere light did not touch the material will dissolve away in water or some other solvent. Anywhere that light did touch the material will remain because it's cross-linked, it's no longer soluble, everything is linked together. You can see this. We start with different photomasks. I'm a big fan of cards, so we use clubs and spades and hearts. These are regions that have the Bottlebrush material that's super soft. Everything else that's gray washed away. So you've got a physical pattern now of these different objects. And you can create flat patterns where you control how stiff is the material. For example, by backfilling with your linear Silgard 184, curing it, and then peeling it off the substrate, which brings along the super soft elastomer regions as well. So now you've got a flat object that has really super soft and harder regions, depending on the photomask you used in different shapes and patterns. You can image this with a different technique called atomic force microscopy, which we have available on campus, where the color now corresponds with how soft or how stiff is the region of the surface. So you can see this is a zoom in of a heart region. It's blue, which means it's much softer. Everything else is more green. It's much stiffer. So I want to change gears now and show you quickly how we can adapt this type of material platform to other processes as well. And we'll focus on 3D printing, which has gained popularity in recent years. There's many different types of 3D printing. I'm going to focus on one called direct ink writing. It's really, really simple. You take a syringe, you load it up with a material that's hopefully a liquid. You squeeze the material out of the syringe and you move the syringe around. And if you design your material depicted in blue correctly, it'll be a liquid in the syringe so you can squeeze it out, but it'll quickly solidify once it comes out of the syringe so that you can control the shape of an object in 3 dimensions as you move the syringe around. And the magic is in designing the material to have this liquid to solid transition as it comes out of the syringe. It's not straightforward to do, but if you can do it and then say, cross-link the solid, and we're going to use the same benzophenone light chemistry, then if you design your material right, you've got an elastomer. And we're going to do this to make really soft elastomers that you can control the shape of using this type of 3D printing. Now, past approaches to shear thinning, again, they're not straightforward. They can be complicated to optimize. We're not going to worry about those so much. We're going to try to design easier routes to get this. And we like a solvent-free process. You don't have to worry about organic solvents, removing them, shrinkage of the structure as they evaporate. And we're going to try to do this at room temperature so you don't have to worry about heating up the syringe, cooling it down, controlling the temperature in any way. To do this, we turn to Bottlebrush copolymers, which have 2 different types of side chains instead of just one. So think about this as all the blue side chains are polydimethylsiloxane, just like we had before. And the red side chains now are a second type of polymer chemistry. And we're going to use polyethylene oxide. There's many different choices. Polyethylene oxide is kind of an interesting polymer. It's used in many biomedical applications. It's actually an ingredient in the COVID vaccines. It's used to improve the delivery of proteins and to provide water solubility in a biocompatible manner, among other reasons. So we're using it simply as a second color or a second type of side chain in our bottle brushes. Now, when you do this, if you pick the chemistry right, like polyethylene oxide and polydimethylsiloxane, they don't like each other. Those polymers, they want to be like your salad dressing. If you mix them together, they would phase separate. They would try to create layers of all polyethylene oxide and all polydimethylsiloxane. But we've linked them together with covalent bonds. So they can't create layers at the visible length scale like your salad dressing, but they try to do something similar at the nanometer length scale, where all of the red polyethylene oxide side chains will bury themselves into little micelles to get away from everything else with this, which is polydimethylsiloxane. And so the polyethylene oxide core of these micelles is of order 5% of the material. Everything else is this blue polydimethylsiloxane. And again, we can control the length of the red and the length of the blue and the length of the backbone. Now, why is this useful? This spontaneous process of self-assembly is particularly useful in 3D printing because these micelles, which you can see how the molecules pack into, actually order on a body-centered cubic lattice. So if you were to zoom in with an electron microscope, you would see a beautiful array of body-centered cubic spheres, which have very characteristic structure. But when you squeeze this thing out of a syringe, it becomes a fluid because the micelles lose their ordering. So they start sliding past each other. And we found that this is really fast going between these two states. When they lose their order, they flow like a liquid. But when you stop squeezing, they really, really quickly snap back into this BCC structure, which is solid. So to kind of summarize what we're doing here, we're using the Bottlebrush architecture to create super soft elastomers. We're leveraging this type of self-assembly with two side chains now to give us this solid liquid phase transition, which is how we're going to 3D print. We use low TG blocks, like we've been talking about all through the presentation, to allow this process to happen at room temperature. Everything wants to be a liquid. It wants to flow at room temperature. And we dope in a little bit of benzophenone, which isn't pictured on the slide, but it's the same chemistry we saw previously because it's cross-linkable, and that will actually create the elastomers once we're done. Now, I'm going to skip this characterization in the interest of time, but we characterize these materials in a variety of ways, including X-ray scattering and rheology like we've seen previously. And I want to jump to this rheology experiment, which is showing you how fast and how efficient the liquefaction is. So what you're looking at here is the stiffness, or that storage modulus from earlier in the talk. And depending on the Bottlebrush sidechain length, the stiffness changes a little bit. These are not cross-linked though. These are still viscous liquids. And as you crank up the stress, imagine like as you apply more force on a syringe, for example, this G prime value drops precipitously and the G double prime value in open symbols increases. And this transition right here is that solid to liquid transition. You can see it's quite sharp. It just happens at some stress that we call a yield stress. Yielding means it goes from a solid that holds its shape to a liquid that does not. And that yield stress also depends on the side chain length. And if you oscillate back and forth between a lot of applied stress or pressure and a low amount of applied stress or not very much pressure, You can see at low applied pressures, the material is a solid because this G prime value is big, the G double prime value is small. You crank up the applied pressure and it switches to a liquid. You drop the pressure back down and it solidifies again. And you do this over and over and over again. And that's exactly what you want for 3D printing. These are a variety of structures we've 3D printed with this material. None of these are cross-linked yet. They're not elastomers, but it gives you a sense of the control over the shape. For example, this is a solid, a hollow pyramid. So the inside of it has no material. You build the outside of the pyramid by going around and around and around, up and up and up, and it stays in the shape of a pyramid. It doesn't just spontaneously liquefy. The example on the right is kind of neat as well. Here's the syringe. You're squeezing it out of the syringe. It's a liquid. As soon as it comes out of the syringe, it solidifies. So this spiral that spontaneously forms, it's holding its shape. It's like floating in thin air. It's actually, held to the syringe, but it's not spontaneously dropping because all of that spiral is now a solid. And if you squeeze more out, the spiral will get a little bit longer, little bit longer, little bit longer. Now we dope in a little bit of that crosslinker with benzophenones. This is the same one you saw in the previous slide. It's blue, it mixes with the blue stuff, and then you can 3D print it. And we'll skip to a video now, which is going to 3D print a bowl. And this has both the Bottlebrush and the crosslinker in it. You can see we'll build out first to create an angled wall going out, and then actually transition and bring that wall back in. It holds its shape. The bowl is not spontaneously collapsing either. Particularly with these angled walls, you've got to have the right properties for your material. You've got to have the right yield stress. Otherwise, over time, it would lose its shape. And then you shine a little bit of UV light on it. And you can see, if you look close, the intensity of the bowl, it looks like it's emitting light. It's actually phosphorescing because when this benzophenone reacts, it creates phosphorescence. And that's a visual cue that it's cross-linking the Bottlebrush materials. And eventually, and you can see the video has stopped now, eventually it looks like the bowl is not emitting as much light when you're shining UV light on it. The phosphorescence intensity has gone down. It's done reacting. Your elastomer has formed. And we'll finish with this picture of the bowl, this video actually, which is now demonstrating the elastic properties. You can put a glass slide on it. There's a little bit of adhesion between the material and the glass slide. And you can see now, as you pull on the bowl, it's really an elastomer. It deforms when you pull on it. It will also deform when you push on it. And if you look close, you can see the individual concentric layers that were used to build up the bowl. Yeah, you can really see them here, but kind of neat. The layers are stuck together pretty well, meaning you can pull the glass slide off of the bowl, off of the Supersoft material without pulling the layers apart. And a lot of the time in this type of 3D printing, the weak point is between the layers because you print those sequentially in different steps. And these actually are held together fairly nice. So with that, I would like to thank everybody for their attention and thank everybody who participated in this research. It's been a joint effort, in particular, a collaboration with Michael Chabanek, who's the chair of the materials department. And again, thank you for your attention. Happy to answer any questions if you have them.
Do we have any questions from the audience? I don't see anything in the chat, so go ahead and ask.
Mary,
Yes.
please.
Go ahead, Mary.
Trying to, okay. I'm really impressed with the ability to do this, Christopher. When you started out, I was thinking of potential medical devices, like something to monitor the pressure in the eye for people who have problems with glaucoma or with AMD. But now you've skipped over to 3D printing and sort of blown me away. So I guess what I'd like to know, there's a problem with 3D printing as I understand it, in terms of toxicity of materials. That, for whatever's being used at this time, and I don't know what's being used at this time. What is there toxicity related to any of this material?
Yeah, so there's a bunch of really interesting questions there, Mary. And let me start first with your biomedical application comment. That's one of the directions we're absolutely going, that we think there's really exciting opportunities with the pressure sensing and with the 3D printing. And we just got an NSF grant to study this, to say, look, how do we personalize sensors for different people in different shapes? So your foot is a different shape than my foot, is a different shape than everybody's foot. If you're trying to monitor pressure, say in a wound on somebody's foot, there may be benefits to using 3D printing to shape the sensor to individual anatomy. Could be the eye, it could be other organs like around somebody's heart. So there's, I think, a really interesting opportunity there. And you're absolutely right that toxicity is absolutely critical, or lack thereof, in order to be able to use these materials in any kind of biomedical application. So I don't know the answer to your question right now. What I can tell you is that polyethylene oxide and polydimethylsiloxane are both FDA approved as materials that humans can eat, materials that can be implanted in the human body. These Bottlebrush polymers we haven't tested yet. They're like 99% polyethylene oxide and polydimethylsiloxane. So are they biocompatible? If I were a betting man, and I do like a good bet here and there, I would say probably. The danger, or the place that, the thing that might not be biocompatible, the ruthenium catalyst that we use to make them.
Yeah.
Ruthenium is probably not good for you. It's used in very low concentrations because it's a catalyst, but it's gonna be there in very low concentrations. And I think that's where we need to focus in experiments on, to understand if it's gonna be a problem or not. And we're working on that right now, although I don't have the answer for you.
Okay, all right. So there is some biodegradability of this product. So obviously the product itself, if it doesn't biodegrade at all, you don't have to worry about the toxicity. You can put it in and take it out, blah, blah, blah.
Well, that's another really interesting question, is that biocompatibility is in some sense distinct from biodegradability. If it's biodegradable, you've got to worry about the degradation products, or those biocompatible, et cetera. Kind of to first approximation, I would say these are not biodegradable. But I think you do still have to worry about potential toxicity, because the ruthenium catalyst at the end of the day is not bound to the polymer. It would be trapped in the material, but it would still be mobile. It would still be a small molecule. It could potentially be extracted by the body out of the material. And so it's possible, even if these aren't biodegradable, it is possible they'll still be toxic.
Thank you.
Thank you for interesting talk. So you mentioned at one point about dielectrics that could be run in reverse and you get energy out, if I understood correctly. I'm just wondering, is there any way to use that to generate energy sustainably somehow?
Yeah, so if you apply a voltage, you'll get mechanical movement out, which it's a form of energy. It's pretty inefficient in the sense that you've got to apply a lot of voltage. This is a class of materials known as dielectric actuators. You can look them up. There's many examples of them. They're really cool, but they require very high voltages. And so I don't think this is an efficient way of trying to solve the world's energy crisis. They may be useful for certain applications, probably not that though.
Along those lines, AFMs and similar instruments use piezos to move the things small distances. Is it in the range that it would be useful for that sort of motion as a piezo kind of thing?
Potentially, piezo is probably more well controlled at lower voltages because they really only need tiny deformations. To give you a sense, people are trying to use dielectric actuators as things like artificial muscles. If you think about the actuation that your hand has or that your arm has when it's moving around, a piezo is not going to be great at that. Potentially a dielectrical actuator could give you much larger strains like that. I suspect it's more well suited for that type of application. Other questions?
I would just
Yeah.
like to compliment you on an exceptionally clear talk. Maybe that's why there are not so many questions.
It
Well-
could go either way, so thanks for that.
Well, the last thing you were talking about, artificial muscles, I've heard about soft robots, various sorts. So this would be applicable to that, right?
Yeah, we're really interested in soft robots. And actually this process, the project started as let's make new actuators for soft robots. And we decided in the course of starting it while we were synthesizing materials that pressure sensors would be easier to demonstrate as just an initial demonstration. But what you're saying, Robert, is exactly what we're ultimately interested in, is a suite of materials for soft robots.
Yeah, I had seen something in the news where you'd have something like a snake or something that could find its way like into building rubble after an earthquake or something. Is that the kind of thing you're thinking of?
Yeah, and I don't know if he's talked here yet. If he hasn't, you might want to invite Elliot Hawks, who's in the mechanical engineering department at UCSB. He's an assistant professor. He does exactly that kind of research. He's developing, it's more from an engineering angle. It's less new materials development, but how do you bring together existing materials to create things like snake robots that can wiggle their way in useful ways into places that normal robots wouldn't be able to, and then come back out with a camera that you control the direction, etc. And we're hoping that if we bring new materials to that area of research, it'll be like a win-win for everybody. And we're really targeting that. So far, it's been a little bit more on the materials development, but we've got a pretty decent handle on that now. We're looking for new applications.
Yvonne, do you know who this guy is? Do you know how to get him?
I'm sure he has an email on the UCSB website. So I've written his name down and put a star next to it. So
You
Good,
said it's
good.
Elliot Hawks?
Elliot Hawks, yeah, I'd be happy to connect you. If somebody shoots me an email, I'd be happy to hook you up with him as well.
sure. Oh, I had some questions about the 3D printing. Do you have to do anything special, like do it in a special atmosphere without oxygen or a heated bed or anything
No.
like that?
Nope, nope. And that's really a concept that permeates a lot of the chemistry we do and a lot of the materials applications. We like to keep things simple. We really don't want to have to create a special environment. You know, these things are all impediments. They're going to prevent people, most people, from using your materials or your chemistry, if you can keep it simple, there's a much better chance that it'll actually have an impact.
Have you had any interest from corporate, licensing, that sort of thing?
Yeah, actually, this whole project has been sponsored by the Mitsubishi Center for Mitsubishi Chemical Center for Advanced Materials, which is called MCCAM, since its inception. They have a center on campus which funds roughly 10 research projects a year. Many of them are multi-year research projects. And as mentioned to Mary a minute ago, we recently got an NSF grant to continue expanding that in new directions. But yeah, one of the really nice things about UCSB is very strong industrial interest in research. And that goes for this project, but many other ones as well.
Great. Other questions from anyone? We really enjoyed the talk. Thank you so much, Dr. Bates.
Well, thanks for the invitation.
Yeah. So,
All right.
thanks. And thank everyone for their responses to the poll. It seems like a lot of people were supportive of, I guess we can share the results, right, Cheryl? Cheryl, if I click share results, is that cool? Yeah, there we go. So a lot of people were in favor of going back into in-person. Can
But
people
I
see
would
that?
say that if you have the opportunity to bring somebody from afar, I'm all for doing Zoom in that case.
Okay. I mean, now that we know how to do that. Yeah. I was doing the Vancouver one before we go back to in-person.
I certainly agree with that.
Who was that?
Bob.
Sorry. Bob.
And
hi,
I
Bob.
do too. Yeah.
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 Okay. Yeah, we'll keep that in mind.
Yeah.
Okay. Hope everyone is doing well. Thank you so much. Good to see everyone.
Bye, everyone.
Bye.
Bye-bye now.
Thanks.
Well.